Hello everybody, here we are at online lecture number 11. Last time we spoke about the rates of reaction and we introduced an equation to express the rate of a reaction. It's a differential equation where the concentration of the reactant A changes over time, and this is expressed by this gradient, and it depends on the rate constant K times the concentration of A times the concentration of B with the respective order parameters. So this part here is basically modeling the probability of the reagent molecules to collide with each other. So that's why it has this concentration dependence. But this part here is a function of different parameters, and we'll talk more about this today. So in order to get a dependency of the concentration of the reagent A, for instance, independence of the time, we have to integrate this. And here we did that for a reaction of first order, so with A equals 1. And the integration gave us this exponential decay of the concentration independence of the time. So we have a starting concentration, Ca0, and then it decays exponentially with this expression. So we then showed that the K value, the rate constant, its magnitude determines how fast this exponential decay of the concentration of reactant A is. And today I would like to ask the question what this K actually depends on. So one important influence on K is the orientation of the molecules during a collision, right? So for instance, let me make it clear. Here we have again this nucleophilic substitution where the hydroxide attacks this bromomethane. And now if I draw the HOMO and the LUMO, so the highest occupied molecular orbital of the hydroxide and the lowest unoccupied molecular orbital of the bromomethane, remember these are the two orbitals that will eventually form the molecular orbital that leads to the reaction. And now if the highest if the HOMO of the hydroxide attacks from exactly this site the LUMO of the bromomethane, then the reaction has exactly the right orientation. The molecules have the right orientation for the reaction to proceed. But if the HOMO comes from another angle, if it comes from this side, then it doesn't really have a good overlap with the LUMO of the bromomethane, and this collision is most likely not going to end up in a successful reaction. So it's not unlikely that only 1 in 100,000 collisions are actually successful where we have the right orientation and overlap of HOMO and LUMO. So it's really a statistical thing. K depends on whether the collision had the right orientation of the molecules. But it depends also on other aspects. So another aspect is the speed of the molecules. So the faster the molecules move, the more often they will collide with each other. That's kind of similar to what we described before with the concentration, but now the speed at a given concentration also affects the collision frequency, right? So higher speeds, usually higher temperatures, you have a faster K value because you have more often the collision taking place. Then, of course, the collisions also, how often they happen depends on the size of the molecules. So if you have really tiny molecules and they will just rush past each other all the time, they won't really meet, even though they fly past each other. But for really big molecules, the chance of them actually bombarding each other, like hitting each other, is much higher. So you can see K also depends on the size of the molecules. So and now a very important aspect is that the molecules, in order to react with each other, they need to overcome an energy barrier. So what is this, an energy barrier? I'm going to explain this based on this mechanical analogy. So here's a block. It's like a block of a metal maybe, and it has a center of mass, this black dot here. So this is the line where the center of mass originally was. In order for this block to fall to a lower energy state when it lies, it has a lower gravitational energy, right? So it goes from a high energy to a low energy state. But in order for this to happen, we have to push it, and then it needs to tip over the corner, And for this to happen, the center of mass of the block needs to increase first. So it goes higher, and that costs energy. So that's almost like an activation barrier. Like you have to first add some energy to bring it to a lower energy. Right? So of course, molecules are not exactly like these blocks that fall and lower their mechanical or potential energy. In a molecule, like the nucleophilic substitution reaction, you have an energy barrier which goes from this energy state of the reactants to the energy state of the products, and the product energy state is lower. So you see this is an exothermic reaction, but in order to get there, you first have to overcome this hill. The energy first needs to increase, and this hill means that the molecule has a transition state that has a higher energy than the reactants or the products. And so the transition state here, for instance, it could look like this, where the hydrogens, for instance, they are moved to more the central plane, and the hydroxide has now attached, and now the bromide, its bond, it needs to be broken, right? So, and this costs energy also to break this bond. So all this is kind of captured in this activation energy, and eventually only you get to these products. So in all of this, it happens along the so-called reaction coordinate. So it's a complicated function of this transition here, that depends on the angles of the parts of the molecules and the positions. So you don't really need to worry about what this reaction coordinate means. It just means this transition here. But you know, some reactions, they actually do not have a barrier. So an example is, for instance, lithium cation reacting with a fluoride anion to form lithium fluoride. And in this case, there's not really an activation barrier, because these two, they attract each other. They snap together because of this electrostatic attraction. So there's no energy barrier because of this. And here's another example of a reaction without an energy barrier. These are methane radicals with an unpaired electron. And if these two unpaired electrons come together, they immediately form a bonding molecular orbital. And so for this to happen, no bond really needs to be broken, and it really doesn't cost energy. You go just from reactant to a product state. But most chemical reactions, they have such an activation energy that needs to be overcome first. So, and how to overcome this barrier? So you can probably already imagine that when the molecules, they collide with each other, now their kinetic energy that they have during this collision determines the collision energy, and this collision energy now is capable of overcoming the activation energy. So it's related to the kinetic energy of the thermal motion of the molecules. And now, if you have, for instance, a gas with many reactants, they don't all have exactly the same speed. Right? The individual gas molecules, they have different speeds. So there's actually a distribution of speeds. Some are very slow, some are very fast. So different speeds, and then only some of the gas molecules have actually sufficiently high energy to overcome the activation energy. Right? So, and typically such an activation energy to overcome is about 10 to 100 kilojoules per mole. But at 25 degrees, the energy of one molecule, the average energy, is only 4 kilojoules per mole. So you see, that's not enough to overcome the energy barrier. But since there is such a distribution of speeds, some of the molecules also at 25 degrees Celsius, they have a higher energy than 4 kilojoules per mole. So even a higher energy than 10 kilojoules per mole. But it's only a small fraction. So typically only 1 in a billion collisions really overcomes the barrier. So you see, this is another thing that affects this K value. So not all collisions are successful. So K depends, as we discussed, on 4 different things here. The first was the speed of the molecule that controls the chance of the collision. The other was whether there's the right orientation. during the collision, then the size of the molecule, the bigger they are, the easier they find each other. And last we discussed this energy barrier. So all of this is captured in this equation that's called the Arrhenius equation. So it has the rate constant K as a function of this parameter A times this exponential term with the activation energy. And here again I plot the energy of a reaction from reactant to product, and the activation energy here is now captured in the exponent. And the entire term, this exponential function, what it tells you is the fraction of molecules or of collisions with energies that are greater than the activation energy, right? So, and you see the temperature is, for instance, here in the denominator, and the activation energy is in the numerator. So the higher the temperature, the more collisions you will have that overcome the activation barrier. And that means this negative expression here becomes smaller, and the smaller the negative expression, the closer this E is to 1, or the smaller this is, the more close to 0 it is, and E to the 0 to the power 0 is 1. So that means K becomes A then. So I explain this a little more, or I repeat myself. So think of, if the activation energy is really 0, there's no activation energy, then 0 divided by RT, any temperature, is always 0, and E to the power 0 is always 1. That means K equals to A, right? If E to the power of this is 1, then K equals 0, equals 1. K equals A, I mean. So that means now we can actually figure out what A is. A is the rate constant in the absence of an energy barrier, right? So if this entire term is 1, that means all collisions are overcoming the activation energy, or all collisions lead to a reaction. Well, no, not all lead to a reaction, but all overcome the energy barrier. Then K equals A, right? So then A is not a function of the activation energy, right? But A now captures the fraction of collisions that have the correct geometry, the correct orientation, the angles, the size of the molecules, and their speed, right? So that's what A is made of. A is these three aspects that we discussed, and E, this function here, is this fraction that overcome the activation energy. So, and approximately you can say that A is independent of the temperature, even though it has the speed of the molecules, which is a function of the temperature, but this dependence is not as strong as the dependence of the fraction that overcomes the activation energy. So let's analyze this equation a little more. So what I'm plotting here is basically this equation against the temperature. So K, the rate constant against the temperature. And now one of these curves is for one fixed activation energy. So, and I increase the temperature, that means this denominator becomes bigger and bigger, and the fraction here goes closer and closer to 0, and then the E is closer to 1, and K gets closer to A. So the K value increases, right? And the higher the activation energy, the higher the temperature is that I have to actually then increase the rate constant. So the same thing from a different perspective now. Just now I plot K against the activation energy, and one curve is now for constant temperature, but the three curves are for increasing temperature. So for instance, here is the highest temperature, this black curve. And now if I have a constant high temperature and I increase the activation energy, then the rate constant becomes smaller and smaller, because with higher activation energy, less collisions will overcome the activation energy. So, and then if this expression here is 0, so at very, very low activation energies, you get A as the intercept of the diagram, of the y-axis. So now You remember maybe last time what we did with the rate laws, and after we integrated the rate law, we linearized it. We linearized it in order to obtain a plot where we can fit our experimental data with. And the same thing you can do with this Arrhenius equation. So I'm linearizing it by taking the natural logarithm of the left side and of the right side. So ln k equals ln a, and ln e to the power this gives just the exponent, right? Plus the exponent. And the plus is also because of the logarithm law. So now I have a linear equation. The ln k has a linear dependence on the inverse temperature over 1 over t. Right? And I can plot this here again. So you see these are lines, and here's ln k on the y-axis, and here's 1 over t. No, I'm plotting here 1 over t, not t, to see a linear trend. And now I have lines that have, for instance, been obtained experimentally. So what you can do, you can measure your rate constant in a laboratory, which you could do by this method that we showed, that I discussed with you last time, where we used the rate law, integrated it and fitted it to obtain a rate constant. And you can then measure it at different temperatures, right? Measure this rate constant at different temperatures. So you get data points here, 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 and you fit them now in Excel again with a linear line. And now the slope of the line is giving you the activation energy, and the intercept of the line with the y-axis gives you this ln A expression, right? So this is a method that allows you to really measure the activation energy of a reaction, of reactant going to this transition state to the products, and also the rate constant, or the rate constant if there would be no activation energy, right? Isn't that cool? You can measure these two parameters based on this model and the linearization, and at really high temperatures, this here is 0, right? 1 over t is 0, and then we are all the way on the left, and then each collision overcomes the activation energy, and you have ln k equals ln A, basically, right? Okay, so now with this knowledge, you should be able to solve homework problem 9.19, 21, and 22. See you later.